This is the equilibrium constant, which is also a K, and it represents the ratio at equilibrium of the concentrations, which is going to be expressed in molarity, of the products raised to their stoichiometric, I know y'all hate that word, coefficients, divided by the concentration of the reactants raised to their stoichiometric coefficients. What in the world does that mean? We're going to write it out as an equation shortly. But now, how you will see it. This K is italicized or a cursive capital K. I will try to cursive. So you may see it as K, or you may see it as K sub C, C standing for concentration. So it is different than lowercase k. Lowercase k represents the rate constant. It is different than capital non-italicized K, because that's a Kelvin temperature. And since it is a ratio, everybody get excited, there are no units. Yay. No units, which is good because we're going to be having exponents. So we're not going to be dealing with like molarity to the fourth. Not going to happen. All right, so let's go back and talk about the law of mass action. This is in like chapter 2 of Gen Chem. You probably learned about it in middle school, maybe under a different name. It is the relationship between the balanced chemical equation and the expression of the equilibrium constant. So when we have our generic reaction, lowercase letters are our coefficients, capital letters are our actual compounds. Products, reactants, double arrow means it can go back and forth. We write the equilibrium constant traditionally from the left to the right. So we assume the reaction is going in the forward direction. So K is going to be, if you go back and read up at the top, products first. So concentration and molarity, reactant C raised to the C, product D raised to its coefficient over your reactants. So that would be A to little a, capital B to little b. So products go over reactants. P comes before R in the alphabet. That's how you remember it. So the coefficients in the balanced equation ultimately become the exponents in the expression of the equilibrium constant K. The equilibrium constant K is not going away. So let's take an actual reaction equation. Notice I've not given you concentrations, but we would write the expression for the equilibrium constant as products. Obviously, if there's no coefficient, it's assumed to be 1. You don't have to put the 1. If it helps you to put the 1, do it. If it doesn't, don't. And then other product has a 2, so it's squared over, there's only, this is a decomposition reaction, so only one reactant, methanol. This is a lot shorter and easier than writing out those Hess's law calculations, yes? Okay, we're not doing summations here. Okay, not in my class anyway. I don't know what y'all are doing in all your other math classes. Okay, so for those of you who are working ahead of me, great. It should look like this. Now, do you remember when you learned how to balance equations and we always said use the lowest coefficients? This is a good reason to use the lowest coefficients. All right, so hopefully you can write an expression. Remember, brackets mean concentration. And unless I specifically tell you differently, concentration is going to be in molarity. There's a thing with pressure that we'll talk about, but almost exclusively concentrations in molarity. Just get excited about that. Now, we can look at the value of K, and its relative value can tell us things about the reaction in general. So the numerical value, it can tell us how far the reaction proceeds and also which direction of the reaction is favored. So when K is much, much less than 1, yes, that's how I actually read those. So significantly less than 1. So we're talking like major negative exponent. So -4th and beyond. That means, look at your expression here. So for K to be really, really low, there's not many products and there's a lot of reactants. So there's a low concentration of products, a high concentration of reactants. If you think about the expression, you can figure this out. You are very smart people. I have faith in you. So that means if you have not many products, lots of reactants, ultimately the reverse reaction, that would be the arrow that is to the left, so the one going back behind is the one that's favored. So it doesn't want to go in the forward direction, it would rather go backwards. When K is roughly equal to 1, that means the concentration of the products is approximately equal to the concentration of the reactants. Again, this is a ratio, products over reactants. Which one? More or less than 1. You can figure this out. It's easier than taking a limit. Now, when it's about 1, neither direction is particularly favored. So when you start the reaction, it's ultimately going to proceed probably somewhere around halfway to completion from the forward direction. Does that make sense? Yes? Good. When K is much, much greater than 1, that means you have a very high concentration of products, a low concentration of reactants. So the forward reaction, that would be the arrow to the right, is the one that's favored. This is what we have traditionally been assuming happens all the time, up till now. All right. Now, let's talk about how we can relate K to the equation using this ratio situation. When reversing the equation, it means you invert the equilibrium constant. You can figure this out. because products over reactants, if you switch it, they flip upside down. The reactants become the products become the reactants. So, taking this generic reaction, products first over reactants. Forward always meaning left to right. If we're to take this same reaction and write it for the reverse reaction, well then, these are our products, and C is our reactant. Look, all we do is turn it upside down. So 1 over K forward. I'm going over this because it's going to be on the homework. Other than this chapter, we're not going to be using this process very much. So kind of hang in there. I will cover it quickly so we can get to more important, useful topics. Now, if you multiply the coefficients in the equation by a factor, so here we're multiplying. If you multiply the coefficients, then remember the coefficients become exponents. So you have to raise, meaning use an exponent, K to that same factor. So if you were to take multiplying this by some factor, n, maybe it's 2, K forward would then be C to the 3 times n, A to the n, B to the 2n. Or you can simplify it out and say all of that from the original equation, not there. That's not a 2. There's the 2. You can do it like that. I think this shows up on the homework. Odds of me putting on a test, very slim. It's an interesting intellectual exercise, not particularly practical. Now, if you add 2 or more individual equations, so think about like a reaction mechanism to obtain an overall equation, then you multiply the K's by each other. So if you have A to 2B, so B is the product, A is the reactant. Just practicing writing expressions.
Is this supposed to be the cursive K?
It doesn't matter. It is a cursive K, yeah, I forgot to change that. I thought I got most of the italics, but I missed that one.
K is raised to n. That's how it's supposed to do.
Yeah. Unless I specifically tell you differently. Which when we get into things with temperature, that's when it gets most confusing, because you have to deal with Kelvin and K, and they're both capitals.
What is it with K?
Somebody thinks it sounds like constant, so they're probably European. And they got Nobel Prizes, so I can't argue with them. I just got to deal with it. So if you add it to your second equation, which would be and B squared. Look, our B squareds cancel out, right? We agree? So C cubed over A. So this is referring to the overall reaction as K prime. So that's your new one. No. This is not a derivative. Not in the calculus sense. It is a derived k, but not a derivative. All right, so k prime is equivalent to k1 times k2. All right, enough with the theoretical for now. Let's plug in some numbers and give this a try. What? K1 times K2? Or when you simplify the expressions, see how those cancel out, b squares drop out? It's a good question. Now, here is the Haber process for the synthesis of ammonia. So this has an equilibrium constant of 5.6 times 10 to the 5th. Okay, so let's do a concept review. Is this a big K or a little k or k about 1? Right here. Is it large, small, or right about 1? It's large. It's very large. Good. So which direction is favored? Forward or reverse? Forward. Okay, good. So if the forward is favored, now this is giving us a fun little exercise here. Make sure I get this right. Okay. Calculate. So we're doing several things. We're reversing it, and we've got some different coefficients here. So, oh, I didn't balance the equation. That's why I messed it. I was like, something's not right there. So we've reversed it, and we've divided it by 2. I was like, something's not right there. Okay, good. Now it is. So we're going to have to do 2 things to get k prime. First thing I'm going to do is I'm going to reverse it. So when we reverse the reaction, what do we do to our original k? Products become reactants, reactants become products. It's a ratio, so we flip it upside down. So to start, let's do the reverse reaction. Again, this is on the homework. Highly unlikely I'm going to put something like this on the test. I haven't written the test yet, though. I'll do it today. No, probably tomorrow. So, what? Yeah, unfortunately. All right, so for the reverse reaction, it's going to be 1 over k. Then, when we multiply the reaction by 1/2, you have to raise k to the 1/2 power. So, k prime is going to be, this is our k, so now we're just going to plug it in. So it would be 1 k prime, 1 over k to the 1/2 power. Plug in your value. No units. Everybody get excited because you know how much I love units. Now, intuitively, since the forward reaction was the one that was highly favored, this should be a small number because the reaction is not highly favored. So, inverse 1/2 power, same as square root if you prefer that. Means the same thing. So this is a small number. I'm going to go with 1.34 times 10 to the 1, 2, 3, negative 3 equals K for our new reaction.